Welcome everyone. Today, we'll explore the various factors that influence corrosion beyond just pH levels. While acidity is a major player, there are many other environmental and material-related aspects that significantly impact corrosion behavior. Corrosion is more than just rust, it's a critical issue affecting safety, reliability, and cost across industries. Understanding what drives corrosion helps us design better prevention strategies. Corrosion is a natural process that deteriorates metals through chemical or electrochemical reactions with their environment. It leads to significant economic losses, safety hazards, and operational inefficiencies across industries such as oil and gas, marine, automotive, and infrastructure. Understanding the factors influencing corrosion is critical for designing effective prevention strategies. Corrosion not only weakens structural integrity but also causes contamination in pipelines, failures in machinery, and increased maintenance costs. Globally, corrosion-related expenses amount to billions annually, emphasizing the need for comprehensive knowledge of its causes. While pH is a well-known influencer, other factors such as temperature, dissolved oxygen, chloride ions, flow velocity, and material properties play equally important roles. This presentation explores these influences in detail, providing insights into mechanisms, combined effects, and mitigation strategies to ensure durability and reliability in engineering applications. What is corrosion? Corrosion is the gradual destruction of metals through chemical or electrochemical reactions. It comes in many forms: uniform, pitting, crevice, galvanic, and stress corrosion cracking. Each type depends on environmental conditions and material properties. Corrosion is the gradual destruction of materials, usually metals, by chemical reactions with their environment. It primarily occurs through electrochemical processes where anodic and cathodic reactions lead to metal dissolution and oxide formation. Common types include uniform corrosion, pitting, crevice corrosion, galvanic corrosion, and stress corrosion cracking. Each type depends on environmental conditions and material properties. Corrosion impacts structural integrity, functionality, and aesthetics, making it a critical concern in engineering. Understanding its mechanisms helps in predicting behavior and implementing preventive measures. Corrosion is influenced by multiple factors, including pH, temperature, oxygen levels, ionic species, and flow conditions, which alter electrochemical reactions and protective film stability. Here are the major influences: role of pH in corrosion, temperature effects, dissolved oxygen, chloride ions and aggressive species, flow velocity, metal composition and microstructure, protective films and passivation, electrochemical potential and galvanic corrosion, environmental conditions. We'll look at each in detail. pH significantly affects corrosion rates by altering hydrogen ion concentration and oxide film stability. In acidic environments, low pH, metals corrode rapidly due to increased hydrogen ion activity, which accelerates anodic dissolution. Conversely, alkaline conditions, high pH, often promote passivation, forming protective oxide layers that slow corrosion. However, extremely high pH can destabilize certain films, leading to localized attack. The pH effect is particularly critical in aqueous systems, where small changes can shift corrosion mechanisms. For example, steel corrodes faster in acidic soils, while aluminum benefits from passivation in neutral to slightly alkaline conditions. Understanding pH influence helps in designing inhibitors and coatings tailored to specific environments. Temperature influences corrosion by accelerating chemical reactions and altering solubility of gases and salts. Higher temperatures generally increase corrosion rates due to faster electrochemical kinetics and reduced oxygen solubility, which can destabilize protective films. In boilers and heat exchangers, elevated temperatures promote scaling and localized attack. Conversely, very low temperatures may slow corrosion but can introduce brittleness in materials. Temperature also affects inhibitor performance and coating adhesion, making thermal control essential in corrosion management strategies. Oxygen plays a dual role in corrosion. It acts as a cathodic reactant in electrochemical cells, accelerating corrosion in aerated environments. High dissolved oxygen levels promote rust formation on steel and increase pitting susceptibility in stainless steels. Oxygen concentration gradients can lead to differential aeration cells, causing localized attack. In contrast, oxygen-depleted environments may reduce corrosion but can favor anaerobic bacteria, leading to microbiologically influenced corrosion or MIC. Managing oxygen levels through deaeration or inhibitors is crucial in systems like pipelines and boilers. Chloride ions are highly aggressive, breaking down passive films on metals like stainless steel and aluminum, leading to pitting and crevice corrosion. Chlorides penetrate protective layers, initiating localized attack that progresses rapidly. Marine environments and de-icing salts are common sources of chloride-induced corrosion. Sulfates and nitrates also contribute to corrosion under specific conditions. Understanding ionic species impact is essential for material selection and protective coating design in harsh environments. Flow velocity affects corrosion through erosion-corrosion mechanisms. High fluid velocities remove protective films and expose fresh metal surfaces, accelerating attack. Turbulent flow increases oxygen and ion transport, enhancing electrochemical reactions. Conversely, stagnant conditions can lead to differential aeration and localized corrosion. Designing systems with optimal flow rates and using erosion-resistant materials are key preventive measures. Material properties significantly influence corrosion behavior. Alloying elements like chromium and nickel enhance passivation, while impurities or inclusions can create galvanic cells, promoting localized attack. Grain size, phase distribution, and heat treatment affect corrosion resistance. For example, stainless steels resist uniform corrosion but may suffer from pitting in chloride environments. Selecting appropriate alloys and controlling microstructure through processing are vital for corrosion prevention. Protective oxide films form naturally on metals like aluminum and stainless steel, reducing corrosion rates. Stability of these films depends on pH, chloride concentration, and mechanical stress. Breakdown of passivation leads to localized corrosion such as pitting. Maintaining film integrity through inhibitors, coatings, and controlled environments is essential for long-term durability. Galvanic corrosion occurs when two dissimilar metals are electrically connected in an electrolyte, causing the more active metal to corrode faster. Electrochemical potential differences drive this process. Common examples include steel-aluminum joints and copper-steel connections. Preventive measures include insulating materials, using similar metals, and applying protective coatings. Humidity, pollutants, and marine atmospheres significantly influence corrosion. Moisture facilitates electrochemical reactions, while pollutants like SO2 and CO2 form acidic films on surfaces. Salt-laden air in coastal regions accelerates chloride-induced attack. Designing for environmental exposure and implementing protective measures are critical for infrastructure longevity. Synergistic influences, mitigation strategies. Corrosion rarely results from one factor. Corrosion rarely results from a single factor, combined effects often amplify damage. For instance, high temperature and chloride presence accelerate pitting, while low pH and high oxygen levels promote uniform corrosion. Understanding these interactions helps in predicting failure modes and designing robust prevention strategies. Effective corrosion control involves multiple approaches: material selection, protective coatings, corrosion inhibitors, cathodic protection, and environmental control. Regular monitoring and maintenance are essential to detect early signs of corrosion. Advanced techniques like smart coatings and real-time sensors are emerging to enhance protection. Key takeaways and references. Corrosion is influenced by environmental factors and material properties. Understanding these helps us design effective prevention strategies for safety and cost efficiency. Corrosion is influenced by pH, temperature, oxygen, chloride ions, flow velocity, material properties, and environmental conditions. Understanding these factors enables engineers to design effective prevention strategies, ensuring safety, reliability, and cost efficiency in industrial applications. References. Number 1, Fontana's Corrosion Engineering is a foundational resource for understanding corrosion science and engineering practices. Number 2, the ASM Handbook provides comprehensive reference material on corrosion topics for engineers and researchers. Number 3, NACE International Guidelines offer standards and best practices for corrosion prevention and control. Number 4, recent research articles on corrosion mechanisms and prevention.